morning session. And the first speaker is Ulisses Barres de Almeida from Centro Brasileiro de Pesquisas Físicas, and he will give us an update on the Southern Whitefield Gamma Ray Observatory, also known as SWGO. Okay, Ulisses.
Thank you very much, Ana Maria. So I hope you are seeing my slides and myself and listening me well. So it's a great pleasure to be here. As we were talking just before the start of the session, I mean, I would like to thank the organizers and Rogerio in particular. This is an experiment, it's a new proposal for an experiment in South America in the field of gamma ray astronomy, very high energy and ultra high energy gamma ray astronomy. And I do think, I mean, of course, there are many good physical, scientific motivations to build such an observatory, which is then promising from the scientific point of view. But I also think that for the continent, it can be a great opportunity for the involvement of various countries and institutions and the collaboration between South American and Latin American groups in this field. So let me apologize. I have a bit of a sore throat, so if I cough a little bit during the talk, I apologize now. So as you know, I mean, astronomy, we are waiting for a number of facilities, or some have already come up, for example, ALMA across the electromagnetic spectrum, that are really going to represent a change, a real evolution in terms of observational capabilities across the electromagnetic spectrum. Not only that, as you can see here indicated, gravitational waves and neutrinos are two windows from the multi-messenger realm, let's say, that have been opened in the past decade. And really, the scene for astronomy and astroparticle physics in particular is evolving really fast and is changing really fast. From the side of gamma ray astronomy, it's very well known. The part that will be played by CTA. CTA will also have we'll have two sites, one in the northern hemisphere in La Palma, where there is a very active volcano going on now, but we also have a very large array in the south hemisphere in Chile. So it's going to be an instrument also present here in the Latin American continent. And I guess it's very clear for everybody what CTA is going to represent, a revolution in terms of the observational capabilities in gamma ray astronomy. But when we talk about ground-based gamma ray astronomy, it's not only CTA and more generally the imaging atmospheric Cherenkov technique that has a part to play. I mean, IACTs are these pointing instruments that observe directly the Cherenkov light that is produced from the extended air showers in the atmosphere. And basically what the technique does is to image the shape of these showers in Cherenkov light in the cameras and do an analysis of these images to separate hadronic from leptonic showers very efficiently, and also reconstruct the shower in terms of the direction of origin of the shower and the energy of the primary gamma ray. But there is another way of studying these gamma ray induced air showers, which is to detect directly from an altitude site the particle tail of the shower. So the particles that reach the ground at high altitude, so the end of the shower, and sample these particles directly with particle detectors. And this is another way in which we can observe gamma rays from the ground, high energy gamma rays from the ground. And the two techniques, they are very complementary. Perhaps the biggest characteristic of the IACT technique is the high precision. So these are really high precision instruments that can achieve excellent angular and very good energy resolution. And because of the observation of the direct Cherenkov light and the high collection area of these instruments, you can reach very low energy thresholds, close to tens of GeV. And this is really the theoretical, the practical limit of the technique, in the sense that below this, the showers that are produced, they are very weak and could not be observed at all. So it really has a wide range up to the very low energies, and the low energies are important for extragalactic and transient sources. But they are really complementary, as I said, and there is one negative aspect of this technique, which is the duty cycle of the technique is really low. I mean, you really need to observe in dark nights, so even nights with moon are a problem for observing the Cherenkov light. So you are restricted to something like 1,500 hours or 2,000 hours at most of observations per year, which is not much at all. So when we talk about the particle collecting instruments, you have the complementary aspect of having a constant duty cycle. So these observatories can detect the showers and image the sources 24/7, and they have a very large collection area and field of view. So they can see one steradian or close to 2 steradians of the sky at a given moment, which makes them really survey instruments in gamma ray astronomy. Because of that, you have long exposures, and you also have a very good background determination. In fact, LASSO, which is the new instrument in this field, can operate basically background free above 100 TeVs, which really means it can observe very weak sources of PeV gamma rays. And the downside of this technique is that because you are only sampling the particles of the shower tail, and the precision with which you do that is determined by the fill factor of the array, the final precision on angular resolution and energy reconstruction is considerably smaller than for the IACTs. But of course, because of this technique being rather cheaper, you can image and you can perform up to the PV. So you're not so limited in energy in the high energy end, but you can really probe up to PV energies of gamma rays. So they are really complementary in most of the aspects that you can think of. And today, the scene of the observatories in the gamma ray worldwide, basically, I mean, you have the well-known Veritas, MAGIC, and HESS, which have been operating for almost 2 decades now. These are Cherenkov telescopes, and you have CTA North and South that are going to be built. And from the side of the particle sampling instruments, you have LASSO, this new instrument in China, and you have HAWK, which is a Mexican-American experiment in Mexico. And what you can see here very clearly is that there is no such instrument in the Southern Hemisphere. And this is the main initial motivation for SWGO, I mean, to have a particle sampling instrument for gamma ray astronomy in the Southern Hemisphere. And what we have seen from these instruments that have been very successful, these instruments that have been operating since the year 2000 and 2005, more or less, is that the sky is full of TeV particle accelerators, or tens of TeVs particle accelerators. This is very common in basically all astrophysical systems, more than one would have expected 20 years ago. And that these very high energy photons, they turned out to be a very important and powerful tool to probe the astrophysics of these objects, but also to probe the origin of cosmic rays in the galaxy and beyond. So today we know something around 250 such sources, but with CTA we expect this number to go to the thousands, really. So this is an image of HAWK, a very compact water Cherenkov detector array in the altitude in Mexico. And here is the sky map of HAWK. So you can see that it has access to around a third of the galaxy, or a third of the galactic plane, more or less. And this is where most of the action happens, at these very high energies above several tens of TeVs. When you compare what HAWK can see, which is this area here in brown, with, for example, what HESS can see and what CTA will see. Of course, CTA is going to reach much further in the galaxy, but the angular range is going to be similar. You can see that perhaps the biggest drawback of HAWK as an experiment for ultra high energy gamma ray astronomy, or very high energy gamma ray astronomy, is the fact that it has limited access to the galactic plane. And in particular, it cannot see the galactic center, where most of the very high energy sources from HESS, for example, are located. And so another aspect that is important in this is that LASSO, this is an image of LASSO, this new experiment in China that has 1 kilometer square in area, has detected, observing basically the same sky as HAWK. This was in the middle of this year, around July, 12 gamma ray sources that are pevatron accelerators, or potential pevatron accelerators. So these guys emit very high energy gamma radiation up to 1 PV or more, And all these 12 sources that have been detected by LASSO, they were detected with a 7 sigma significance. So it's really the tip of the iceberg. And among them, you can see here the Crab Nebula, which was detected beyond 1 peta-electron volt in gamma rays. So this highest energy photon here comes from the Crab Nebula. This really established the Crab Nebula as a very efficient PV accelerator, electron PV accelerator. So basically, the Crab Nebula is a perfect accelerator machine when we see the physics going on behind this acceleration. And you can see here very clearly the two components of the LASSO detector, the water Cherenkov detector here at the center, these large water pools, and the kilometer square array, which is basically an array of scintillators and buried WCDs for detecting the muons. And that's what gives it the possibility to operate background free at these energies. So the two sides of this experiment, the two components really operate together to allow this very large dynamic range of observations that go from a few TeV up to 1 PV. And you can see here an example of some of the sources detected by LASSO, some of these PV accelerators. Some of them are resolved, such as the one in the middle, and you can see they are extended objects. And they are relatively strong, but of course, although there is no cutoff apparent in these images, the spectrum is very soft. So they fall very strongly with energy, which means that you do need a very sensitive detector to observe these kinds of objects. Of course, the significance of observing PV accelerators is to nail down, is to understand the origin of the galactic cosmic rays, and especially the origin of the near cosmic rays, which are of PV particles. So the sky seen by Hawke, as I said, is limited to just a part of the galaxy. But an experiment in the south would not only be able to see most of the galactic plane, thus complementing what can be done from the north, but really observe the galactic center and other structures interesting like the Fermi bubbles, which are these huge particle reservoirs with up to 10 to the 56 ergs in energy, if protons are the dominant particles there, that are stored in these bubbles, likely coming as the result of past activity over hundreds of thousands of years of our galactic center, of the AGN in the galactic center. So these are very interesting science cases. And of course, the business of the pevatrons and understanding the acceleration of particles and high energy cosmic rays in the galaxy really depends on a good census of this PV population. And this is a major motivation for having an observatory like SWGO built in the south. So here you can see for the reference configuration of SWGO for 1 year integration and for 5 years integration, and those 3 LASSO sources that I just showed. So this is their spectrum. And you can see they are strong, and for sure, an observatory like SWGO will be able to detect several of these sources in the south. But of course, to go to the highest PV energies, there is a lot of work to do because the spectrum falls out very strongly. I'm going to comment a little bit more on this high energy extension later. Dark matter is another thing, is another area in which an experiment like SWGO could do a very significant contribution, in the sense that the galactic center and halo, they are the most promising regions where to search for dark matter signatures in gamma rays. And here you can see the WW WIP model channel, and you can see here the sensitivity curve for CTA and the sensitivity curve for SWGO after 5 years integration. So you can see they're complementary. So whereas CTA will do very well in the observation of or imposing dark matter limits or searching for dark matter from the galactic center around the TeV or tens of TeVs. Above that, SWGO will be able to complement and probe the highest energy modules if they turn out to be interesting to search. So even in the dark matter regime where CTA is a major player, an instrument like SWGO is very welcome to complement the potential of CTA. Not only in this high energy domain, let's say, but also in the variable source, the transient realm, SWGO should play an important part. So the first obvious thing is the transient synergies with CTA. So CTA is a pointing instrument, so it has generally to look for transient sources or to observe flares or GRBs, it has to be triggered. And an instrument like SWGO, observing a very large portion of the sky, 1 steradian or more, above tens of TeVs, will certainly be able to trigger CTA on a number of sources, including GRBs. And GRBs are particularly interesting in the sense that they have recently been observed at these energies. Here you can see the first of those, which was observed by MAGIC up to 1 TeV. And although these instruments can observe VAG emission from the afterglow of the GRBs, since they are pointing instruments and they have to be triggered, they have no chance of observing the prompt emission, if there is any prompt emission at the TeV range. So SWGO, by again observing a large portion of the sky, surveying the sky, could have some hope of observing the prompt or the very early afterglow emission of GRBs. And this is particularly interesting when you think of the multi-messenger scene, where short gamma ray bursts are counterparts to gravitational waves. So SWGO could have a chance of observing those and therefore making a bridge from the electromagnetic, very high energy electromagnetic to gravitational wave messengers. Neutrino is another field in which SWGO, but other experiments like LASSO can have an important synergy with. So by mapping the diffuse emission and really separating the inverse compton from the pi-decay components of the diffuse emission of the galaxy, we can add some information to understanding the content of neutrinos in the galaxy, and also of cosmic rays as a consequence. But the really interesting thing is that whereas LASSO and HAWK are complementary to the observations that IceCube does, there is no instrument that is able to complement the future facilities like KM3net. And SWGO, being in the south, will be able to do that. So it's an important complement for synergies with the new neutrino instruments that are coming up. So this was for the scientific motivation. As you can see, there is a lot of reasons for why to build an instrument like SWGO in the Southern Hemisphere. And so the collaboration was started in 2019, and we are in the middle of a 2-year R&D phase. We currently have 47 institutes in 12 member countries, plus a number of supporting scientists from different countries. Particularly, the Latin American involvement is very large. So I point here the country representatives for each of these 5 countries, five Latin American member countries: Mexico, Peru, Chile, Argentina, and Brazil. And the collaboration is really growing and is really welcome to more collaborations, and especially from Latin American countries, since this is going to be an experiment operating in our continent. So this is a drawing of the main concept of the observatory. The idea is to have a very large area from at least 200,000 square meters up to the kilometer square range, covered with water Cherenkov detectors, to sample the particles from the air showers. And as you can see, the idea is that we have a very compact core with a density of stations of up to 80% fill factor. And this is really to be able to have a good angular reconstruction and a low energy threshold, as low as 1 TeV or lower, to be able to image and do this transient science that's basically happening below the 1 TeV or few TeV regime. And then the experiment should follow a graded approach in which you equilibrate the fill factor and the area covered, balancing the costs of the experiment. And so here in the main concept, the idea is to use tanks, but actually the mechanical concept is quite open for the observatory. As you can see, tanks is the main design, and it could be steel tanks or plastic tanks like used in Auger. Steel tanks are what is used in HAWK, for example. But since in Peru there is many high altitude lakes, there are some considerations on the possibility also of installing these detectors directly in a natural lake, or if the thing proves to be quite promising, you can even think of building artificial ponds to host the detectors. And so this is a new concept that hasn't been used before, particularly the operation in a lake, but it's something that we are strongly looking to, as it could save costs if it proves effective also in terms of maintenance and operations. So regarding the sites, the observatory has to be in the Andes and has to be in South America as a consequence, because we really need to be at an altitude site of at least 4.4 kilometers above sea level. So the Andean region is the only place where you can find these altitudes in the southern hemisphere. And within this, we have sites in various countries, and it's actually a large number of sites. It's 8 to 10 sites that have been identified. And we are currently in the business of evaluating these sites and applying a first shortlisting. So you can see some pictures of these sites. So most of them are large plateaus, very, very flat, that can accommodate a kilometer square detector. But there is also, as I said, some altitude lakes in Peru. And this is an image of the beautiful Lake Sibinacocha at 4.9 kilometers in altitude, which looks really a promising option to be investigated for this new type of design. So as I said, we are doing site characterization. Of course, this has started very slowly because of the pandemic, so we couldn't do site visits yet. But with the help of the local teams, we have collected quite a bit of information to do an initial shortlisting of the sites. And most of next year, we should spend visiting the sites and doing real characterization in order to be able to make a site choice within the next 2 years. So this is a drawing of the reference configuration of the observatory. So a very dense core, 80,000 square meters in size, with a fill factor as close to what is possible for having access to the individual units of 80%. And then a considerably lower fill factor, but it's still high for a large detector of circa 200,000 square meters. So this is our reference configuration, and it's really the minimum configuration that we want SWGO to operate on. So the idea is to identify ways in which we could work with the technology and make a larger and an even more sensitive array than this reference configuration during the R&D phase. And also our reference configuration unit is a double layer water Cherenkov detector. So basically we have an upper layer that does the calorimetry of the electromagnetic component, and a bottom layer to detect the true going muons, because mu identification is a key element of background rejection. So it's one of the most promising ways to tag the hadronic showers and do the gamma hadron separation and hadron rejection that we need. But we are investigating other unit designs. In particular, I mean, this reference configuration is very high. You have here over 3 meters in height of water. And of course, in these regions, except for the regions where there is a lake, water is a very scarce resource. So a significant part of the cost of the experiment should be on water. So if you can operate with smaller tanks and therefore lower quantity of water, this makes a big change for us. Remember that the detector should have something like 5,000 to 6,000 detector units, which means something like 10 to the 5 cubic meters of water, if I'm not wrong. So it's a very large amount of water. And one of the options is to make shallow tanks using multi-PMTs. So not only one, as shown here, but to spread in a geometrical arrangement the PMTs in the tank, so that you can detect the first light of the particles entering the tank and use that with some clever analysis chains to identify the muons and therefore tag the muons from the signal they leave in individual PMTs in order to do the gamma hadron separation. So this is new, this is still under investigation, but it's a promising option. And in any case, in the R&D phase, we are looking into various detector options. And again, the idea is to establish a plausible and realizable in terms of cost design for the observatory that allows us to cover the largest area possible and with the highest density of detectors within a reasonable cost. One of the frontiers that we pay a lot of attention to in the reference configuration is this low energy frontier. And this is basically achieved by having a large detector array, so considerably larger than HAWK, for example, which is 20,000 square meters. So already the inner part of our detector is 4 times the size of HAWK, plus you have all the extended area. And also the increased altitude. So by approaching the 5 kilometers altitude, we are able to reduce the energy threshold of the observatory quite sensibly and operate with good precision below 1 TeV, which is really important for the transient science we want to do. And this is an image of the phase exploration that we are working on with SWGO. So this is the reference configuration, which we call a Strawman model. This is 1-year integration. This is the sensitivity of HAWK for 500 days. And this is compared the sensitivity of LASSO. So this is the WCD, those ponds in the center of the array. And this is the extended array that I talked about, which is responsible for the Pevatron detection. So you can see that the reference configuration is in itself a good match for the WCD of LASSO, but we really need to expand a lot to be able to match what LASSO does at the PV or the ultra high energy regime. In any case, all this yellow band is within our investigation realm, and particularly to enhance the low energy capabilities with respect to the reference configuration. We can also improve the general performance by improving the PSF and background rejection. And this part here can only be achieved by increasing the area of the array. So we are exploring kilometer square configurations, which is 5 times in area what the reference configuration is, in order to achieve the PV sensitivities necessary for Pevatron studies. And another important thing—
You have 5 minutes, Ulisses.
Okay, thank you very much, Ana Maria. I'm close to the end. So, and another important thing where we want to expand from current experiments is on the precision of the shower reconstruction. So by having a very dense detector at altitude, we are able in principle to sample the showers much better. And this could allow us to reach a much lower angular resolution, which is very important for resolving these extended sources, and therefore to more strongly or more properly match the sky maps with the lower energies. For example, the sky maps from CTA with the sky maps that we are going to make at the very high energy. So this will allow us to really understand the high energy extension of the sources and avoid confusion. And just to finish, this is my last slide. With a good muon tagging capability, SWGO should be able to do good cosmic ray studies. In particular, we want to have an unprecedented mass separation potential of 3 to 4 mass species around 100 TeV. And this is a region where we can contribute a lot for composition studies and for mass-dependent anisotropy studies. And so this is a component of SWGO that well departs from the focus of the gamma ray analysis, but will surely be important also to complement the joint studies that have been done between IceCube and HAWK, and will surely be done between IceCube and LASSO, closing the latitude gap that exists for a full study of the sky at these hundreds of TeV energies for anisotropy studies. So as the conclusions, there is a clear need and a large scientific potential for a wide field of view instrument operating in the VEG to ultra high energy regime in the southern hemisphere. So first of them is the complementarity with LASSO, and to provide a full view of the sky in the TeV to the PV regime. And this will be very important for narrowing down the population of PV cosmic rays in the galaxy, so the near cosmic rays. And strong synergies with CTA are an important aspect, not only in the high energy domain galactic science, but also in the transient scene, where SWGO should be an important player in the multi-messenger arena. SWGO is halfway in its R&D phase. We expect to do the site shortlisting by the end or early next year, actually, and to have a final site choice and detector definition within 2023, when we expect to conclude the R&D of the observatory. And of course, and I cannot emphasize this sufficiently, we are really looking forward to strong collaborations, especially among the Latin American countries, and new partners and new ideas are very welcome. So thank you very much.
Okay, thanks very much, Ulisses, for this interesting talk. We have time for questions. So if you have questions, please raise your hand. I see Rogerio, you have your hand raised. You have questions?
So Ulisses, thank you very much for this great talk. It's an amazing project. I just want to ask you about the technological challenges of this project. If you can say, what are the biggest ones?
Right, so I think if we could see first the big picture, I think the greatest challenge is to build a detector that's going to be installed in such high altitude and an isolated place, which means that it's going to be a very low maintenance detector. So we have to be able to build a performing instrument that really is basically standalone. The idea is to operate SWGO for a couple of decades at almost 5 kilometers above the sea level. And maintenance costs are a big aspect we are looking into. And the second thing I would say is this thing of the water. So really limiting factor in terms of the cost is if we need to recourse to large tanks. So one of the main goals that we have is to be able to reduce the amount of water that is necessary as much as possible, because this is going to impact a very important percentage of the cost. And this new idea of the shallow tanks is very promising in this regard. Is particularly something that we here at CBPF are working directly on with other collaborators. And but it has never been done. I mean, to detect muons only using the asymmetry of the light deposition in the tanks. And this is an analysis challenge, actually, more than a hardware challenge. In addition to that, I guess one of the options that's very promising is the lake, and but it's something that has never been tested. So the installation of such a detector in the lake has lots of big question marks on the durability of the components, the stability of the components. How can you calibrate things considering the movement of the water and the relative movement of the different units? But if we could solve those problems and make a reliable detector that can operate in the lake, this means that the costs could be potentially much lower, of course, if maintenance is also lower. So this is another front. And of course, there is many other challenges from the point of view of electronics and the photosensors. But I guess that at this moment, we are really looking into approaching these large mechanical configurations of the detector, on which big decisions lie for the whole configuration of the instrument. And some of them are really new, have never been done. And so it's the main focus where we are concentrating our ideas, I guess. I don't know if that answers the question.
Yeah, thank you very much, Ulisses.
Okay, any more questions? Edgar?
Hi. Thanks a lot, Ulisses, for this wonderful talk. I have two questions, actually, maybe kind of naive, but is there a minimum latitude for this new experiment in South America? And that's the first one. And the other one is about prompt emission. Is there a way that you can trigger on that? For instance, I don't know if people do this in these experiments, but do satellites in sync can help with that? Is this an option, or I'm totally off?
So regarding the latitude, yes, we have set, as you could see from the map, latitude range higher than 15 degrees south, or actually between 15 and 30 degrees south. And this is so that we can always have the galactic center at a low zenith distance, which is important because that's one of our main sources. So to go closer to the equator from that is not ideal, and to go further from the equator, from the 30 degrees, is also not ideal, because then you lose a good overlap region for joint studies with LASO, for example. That may be important. And regarding the GRBs and the prompt emission, of course, all these things are done in coordination with other bands. So for sure, and that's what we do now. Satellites are the triggers for example, observations by CTA or other ground-based instruments, and basically observations come from SWIFT or Fermi. But so the triggers come from SWIFT or Fermi. But the thing with SWGO is that it will be able to give a trigger from higher energies, which may turn out to be interesting. But one of the things that we do want to do is to open this prompt regime to the very high energy observations. And this is something that is completely closed with the ACTs because of the pointing instrument. I mean, you need at least 30 seconds to point an IACT to a source. So the only hope that you can have to observe these very high energy sources like GRBs at the onset of the emission is with this large field of view instruments. So I guess the point here is really to emphasize the fact that we want to open this window for the prompt emission with the VAG observations.
Okay, thank you.
Any more questions from the people around? Okay. Well, if not, I have a maybe naive question also, Ulisses. If I have understood correctly from other things, I thought in the Pierre Auger Observatory could also detect these very energetic gamma ray bursts, and they are also in the southern hemisphere. So I wanted to know how these two, if these two are complementary or completely different.
Well, Auger, it focuses on the detection of the hadron component of their shower. So it's a cosmic ray observatory, whereas here we are really aiming to detect the gamma rays. So in this sense, they are very complementary because they are looking at different components of the emission, astrophysical emission. So I don't know if I answered.
Okay, and yeah, one more question that I don't know about the funding. Who is funding this project?
So for the moment, there are individual small fundings for R&D from the various participating countries. And last week, we had a good review in the Astro 2020. SWGO was placed very high in the recommendations of Astro 2020, basically at a par with CTA, which is the other experiment in the field. So, I mean, we are in a phase of R&D where we are designing the experiment and we are building the momentum within the community and building the science case of the experiment to really then, with defined project, look for the let's say the big funding that is going to build the experiment. But for the moment, we are just in the R&D phase and starting some prototyping. So funding is basically national from the various countries and of modest size.
And when do you think it will start operating? And when is it planned to start?
So if we manage to finish as is in the schedule, the R&D phase, so the design of the observatory and the choice of the site by 2023, so in 2 years' time, we would have to go through a phase of looking for funding and doing some engineering array with the chosen detector technology, which should take between 1 and 2 years to then start construction. And so we would be starting construction around 2025, 26, and you can foresee 2-3 years of construction where we could for sure start operating as we deploy. So with subset of the detectors. But so this is for after 2025, 2026.
Okay, are there any more questions?
Which actually coincides with CTA. I mean, CTA should also come online around the same time.
Well, then best of luck.
Thank you very much.
So if there are no more questions, then we thank Ulisses again for the very interesting seminar. And now we are ready for the next speaker. So